The second lecture today. Last week, I hope you remember, we talked about, well, what BPM is about, what business process management is about. And we also started talking about the process discovery phase. We had a long discussion, or well, not a long discussion, but we had some insights regarding the first phase of the life cycle, the process identification stage. Remember, that's the only stage in the life cycle where we basically still talk about many processes, while now we already moved towards the unit of analysis being a single process. So we are in the process discovery stage, and we already looked into mainly elicitation techniques. I hope you remember that from last week. So we looked into all kinds of 5 different types of elicitation techniques in order to start modeling the process as is, because that's actually what process discovery refers to. So this information elicitation regarding the process is crucial. The next step in this process discovery stage is modeling the process. So that's actually, for this lecture and for next lecture, the topic of the lecture. We will talk about process modeling. We will talk mainly about the business process model and notation, something that most of you, but maybe not all of you, were already introduced to, either in the BIS course or in another course. But I guess that some of you already are familiar with most of the BPMN syntax. And that's what I will do today, but I will start off with a more general introduction into process modeling. As always, I have the references to the 2 books that I use. Remember, these books are used rather as background material, definitely not as the core study material. It's background material, supplementary to the slides and what I explain in class. But for instance, also the chapter 3 in the process mining book that I mentioned here, it's a very technical chapter, but it contains some deeper information, some more concrete information regarding some of the aspects that I will talk about today. It's not that you need to know those, but for those of you who are interested to know a bit more, who want to know a bit more to understand everything, it could be good to have a look at those chapters. All right, before I come to BPMN, I would like to broaden the scope a bit and talk about modeling languages in general. I mean, what we basically need now that we have collected all the information in order to build a process model, in order to design a model that describes the as-is situation, we need some kind of language. You should remember, I hope you remember, that the BPM domain, all the techniques, all the stages of the life cycle are centered around this key concept, which is a process model. So the model itself is the center, is the cornerstone of every other action or technique that you do in process management and in the process management life cycle. So we need a good language to construct this model, and that's where we have actually plenty of languages available. Right? Here you see an overview of some of them. We have, for instance, also UML activity diagrams, which are often used in practice, which you might have come across already. In this course, I will limit myself, except for maybe 3 or 4 slides later on, to PetriNets and BPMN. Why PetriNets and BPMN? Well, I explained it in detail in this slide deck. BPMN mainly because it's the leading tool in practice. It's a leading language in practice. It's the most often used language in practice. And PetriNets because I need it partially for the process mining chapter of this course, as well as it gives you a very good basic understanding of what such a modeling language needs to do, what the function is. And it's also, to some extent, a good primer for learning to model in BPMN, because some of the constructs and some of the aspects of how you look at the BPMN model are very similar, or the logic is quite similar to what we do with PetriNets. I mean, PetriNets is a very, very obvious language in order to use, and that will become clear hopefully already after this session. So that's what you need to remember. We will talk about PetriNets and BPMN in specific. Why do I use PetriNets? What is the reason that I also introduce PetriNets? Well, I already mentioned it. It's also because I need this language later on in the process mining sessions, which are the 4th, the 5th, and the 6th session of this course. But PetriNets in general are a very, very useful language for modeling all kinds of dynamic systems. Actually, the main advantages of Petri nets are represented on this slide, and the most important advantage of Petri nets is the fact that they are entirely mathematically founded. They are, I mean, whatever you model in Petri nets, there is no, how should I say, there is no discussion about which behavior that you're modeling, right? So to interpret into a business process, if you use Petri nets as a modeling language, there cannot be any discussion about what kind of variation, behavioral variation, you model, right? That's different with, for instance, even a language like BPMN. BPMN contains constructs that, in terms of the control flow, remember this concept, control flow, how activities relate to each other over time, leave options for interpretation, let's say, right? There are elements in BPMN that can be used and that make it kind of fuzzy of what exactly is meant with the control flow or what should be the executions that can be allowed. While in Petri nets, that's completely not the case. This is a language, whenever you see a model, everyone will know exactly what behavior is being modeled. There is no doubts about whether a particular execution variant could exist or not. No, it's entirely mathematically founded, so it's 100% sound, 100% correct, right? On top of that, another advantage of Petri nets is that the symbols that are used, the set of symbols is extremely small. We basically use 3 symbols, and that's it. We use places, transitions, and arcs. That's also very different from BPMN. I mean, I don't know whether you remember something about BPMN, but one of the things you could remember is the BPMN poster that is often used. Well, it shows like the entire set of BPMN elements, which is, I mean, it's insanely, it's an insane amount of modeling elements for anyone to remember, let alone to use, right? So in Petri nets, there is an advantage that the modeling elements, in terms of the amount of them, is very small, which makes it a very convenient modeling language, which also makes that the models that you build are quite compact. So the language is small, or the notation is small in terms of elements, but it's also leading to quite compact elements, or compact models, I should say. On top of that, in terms of processes, in terms of business processes, these Petri nets allow for all the kinds of behavior, concurrent behavior or parallel behavior, local choices, whatever, all kinds of behavior that you might foresee in a business process can be modeled through Petri nets. So it is a good language. It's even the case that Petri nets are used for way more complex dynamic systems than business processes. But I will come to that in a minute. And then a final advantage is actually the combination of the two figures on the right-hand bottom. Petri nets, given the fact that they're also applicable in many other domains, have a very large set of tools. There is a very strong tool support, analysis techniques, automated analysis techniques that allow you to work with these Petri nets, right? And that's also an advantage for process modeling in the sense that it can be easy to model a process in Petri nets because there is tooling available. On top of that, because of the mathematical foundation of these Petri nets, it's sometimes very easy to check characteristics of your model. For instance, is this model syntactically correct, right? Doesn't it contain deadlocks, for instance? Is a question that is easily answered because there is lots of tool support for it. If you have a BPMN model, well, some tools already have support regarding syntax checking and so on, but it's not default. It's not always default, and it's not always as good as the syntax checking tools that you find for Petri nets. So these advantages make that Petri nets, definitely in research, in the scientific BPM community, Petri nets are very often used, right? Whatever we do in research, we often rely on Petri nets in order to do our research, especially also in process mining. These are, because of their mathematical foundation, they are often used. In practice, it's less of an advantage to use them, but I will come to that in a minute when I explain the advantages of BPMN. So, let me first explain what these Petri nets are, because I think for most of you that is something quite new. Here you see, I will do it by example. I will introduce, I mean, I don't expect you to know the really formal definition of Petri nets. I just want to do it by example. But basically, a Petri net system or a Petri net consists of a set of elements or sets of elements. The sets are called P, T, and F, right? So it's basically a relation between three sets, and then you also have M0, which is the initial marking. I will come to that in a minute. But it's basically P, T, and F that are important first. Those basically represent the structure of the net. The markings are used for the behavior, but the structure of the net is based on the set P, the set T, and the set F. So those are sets of elements. Now, what are these sets? The set P is a set of places, visually represented by these circles. By these circles. So start, C1, C2, C3, C4, C5, and end are the places of this Petri net, right? That's what we call a place. So the model consists of a set of places. In this case, we have 7 places. The next set is the set T. That's a set of transitions. Those are the rectangles in my model. So the A, B, C, D, which I now mapped to particular business activities to give it a bit more meaning. But so transitions, the set T, is the set of activities that can be executed if this would represent a business process, right? So that's what we call transitions or activities. But in a Petri net system, we usually talk about T, so transitions. And then finally, the set F is a set of flows, or also referred to as arcs. And those are all the arcs that you see in the model. Those arcs or flows connect transitions and places with transitions. Note that in such a model, with a flow or with an arc, you can never connect a place to a place or a transition to a transition. You can only have arcs that go from a place to a transition or from a transition to a place. But never, ever you will see an arc that goes from one place to another place or from one transition to another transition. Okay? So that's the structure of the model. The structure obviously defines the potential behavior, but the actual behavior is modeled through so-called tokens. Tokens can be present in the circles, in the places of my model. In this case, this place contains a token represented by this black bullet here, right? This black token. Those tokens will represent the behavior of the model, or the state of the model, to be more concrete. So the state of the model is represented by a distribution of tokens across the different places in the net, right? So in this case, in this initial state, which we call the initial marking, we have one token in the start place, right? So this makes that my model or my process is in the starting state. Now, the behavior or the execution of Petri nets is governed or is determined by the so-called execution semantics or firing semantics. This slide explains these firing semantics. It's not more difficult than this, but this explains how a Petri net basically models behavior or represents behavior. What does it mean or what does it state? Well, it states that a transition, so one of these things, can execute or fire in terminology whenever all the input places of this transition contain at least one token. So, to come to the bottom part of the slide, we have transition A having one input place, so one place for which the arc goes into A. This is called an input, the only input place of A. It contains a token which states that transition A fires. As soon as we have a token in all the input places, A is executed. By executing A, by executing transition A or firing transition A, you consume a token out of every input place. So you'll consume this token and you produce a token in every output place. You can see that in this small example, transition A has 2 output places. Well, in both of the output places, you need to put a token, right? In order to allow for next behavior, next states to be reached after firing other activities, for instance, B and C, right? So let me show that in a model. So it's very important for you to understand the rule. As soon as you fire transition, you consume a token out of every input place and you produce a token in every output place of a transition, right? That's the idea. So let us look at an example. You have to remember my story from last week where I stated that the process model is an abstraction over potential types of executions, right? Different types of executions. What I will now show with this model is one particular execution. But I will immediately show that other executions are possible. You can make other choices generating another type of execution sequence. And that's why this model is a model, right? Because it basically groups different types of executions into one visual representation. But in order to show these firing rules or these firing semantics, I would like to give one single example. We always start in the initial marking. The initial marking meaning you have a single token in the start place, right? Well, which activity or which transition can I execute now? Obviously, only a register request can be executed. What will happen if I execute register request? Well, you consume the token in start, and you produce a token in both output places. What are the output places of this transition? C1 and C2. So that's what we get. This is called the second marking, which I now denote as the marking 1. And the marking notation just indicates which places contain a token. So in this case, my marking is denoted as C1, C2. Note that my previous marking was just denoted as start, right? So this is the marking. Marking 1 is denoted as C1, C2, meaning C1 and C2 contain a token. Now, next question. Which transitions or transition are enabled or can execute, given this state of the model, given this marking? Examine thoroughly, that's definitely one of them. Examine casually and check tickets, right? So 3 transitions are enabled. I can now choose. I can make a choice. I can do check ticket, I can do examine casually, I can do examine thoroughly. Suppose that I choose to do examine thoroughly. What happens to my model? Well, you need to consume the token out of C1. So in order to execute this, you need to consume the token out of C1, and you will produce a token in every output place of this transition, which is C3. So this will happen, right? So the state of my model updates to, or the marking updates to C2, C3. Note that this construct here at the top, this construct here, meaning that we have a single place connected to multiple transitions, actually depicts a choice. I need to make, this is basically Petri notation to model a choice between activities or transitions. I do either examine thoroughly or examine casually. As soon as I do examine thoroughly, the token is removed here and I cannot do examine casually anymore. Yeah? Do you see this? Right, so this is the next state of my model. Now, new question, which transitions are enabled or which transitions can I fire? Decide? Everyone agrees? Decide is not enabled. Decide is not enabled yet. Why? Well, the rule states that you need a token in every input place. In every single input place. C4 is also an input place for the transition decide, and it has no token, so decide cannot execute yet. The only transition that you can fire in this state of the model, from this marking, is check ticket. Check ticket can be fired, you consume the token in C2, and you produce C4. Before I continue, one further remark. The construct that you see here, after register request, 2 outgoing places, this is actually denoting a parallel construct in a Petri net. You can see this clearly. This top part, this choice between examine thoroughly and casually, is logically and control flow-wise unrelated to the lower part, which is the check ticket part. Right? So they can interleave, as we call it. We could have done check ticket first, and that's possible. There is no strict relationship between check ticket and the examine activities here. So this part of the model, so this transition register request with its two output places, actually models a parallel construct of the process, a parallel behavior of the activities that follow that particular construct. All right, so we're now in this M3 marking. C3 and C4 have a token. Next, we can indeed fire decide. We can execute decide. And when you execute decide, remember again, you consume a token from every input place. So it means that both C3 and C4 lose a token, or you consume both tokens. And you produce a single token. You don't produce two tokens, you produce only a single token, right? It's not because you start with 2 here that you will also obtain 2. That's not how these firing semantics work, right? You always have to think in terms of consuming 1 out of every input place and producing 1 in every output place. It doesn't matter whether you start off with 10 places and 10 tokens and you only have 1, or when you have 1 and you obtain 10, it doesn't matter. You don't have to count the tokens as such, right? You don't have to have the same amount of tokens in a firing that follows. So here we fire decide, we get the marking C5. Which transitions are enabled now? Pay compensation, yes. Reject request, and reinitiate request. So we have basically a choice between 3. Again, a construct that we would denote in BPM with an XOR split, right? Suppose I choose for pay compensation. In that case, I reach the so-called end state of my model, the end marking, which is basically only marking with a token the end place, right? So this is a single execution of my model. Obviously, I can do several executions. I could have made different choices. Actually, how many executions could I do? How many different executions are there in this model? How many? Infinite, exactly. There's infinite amount of potential executions. Why? Well, because of this reinitiate request loop. Like this loop, the fact that we, from the marking with C5, so the previous marking, we could go back again into the marking C1, C2, makes that we can basically loop eternally, right? So there is no limit on how many times you loop. So therefore, for this type of model, and basically any model with a loop, we state that there is an unlimited amount, an unbounded amount of firing sequences, right? That's why we call them firing sequences. All right. So the firing sequence can be represented by the markings, as I do here. So a firing sequence can be said like we have marking M0, M1, M2. That's a firing sequence. You can also list the transitions that you fire. That's the equivalent notation. You can say register request, examine thoroughly, check ticket, decide, pay compensation. That's my firing sequence in terms of the transitions. You can both denote it in terms of markings as well as transitions. It's exactly the same. It contains the same information, right? Petri nets can be used for all kinds of dynamic systems. Here I show a dynamic system of a tunnel system, in which a maximum amount of cars can enter the system and can enter the tunnel and so on. So you can model very, very difficult things, complex dynamic systems with Petri nets. We use in process modeling, we use a restricted class of Petri nets. This restricted class of Petri nets, we call them workflow nets. Workflow nets are those nets, or are Petri nets, which attain to a certain number of characteristics, and those are basically the 3 that are listed here. We state that a Petri net is a workflow net, and a workflow net is the only very good type of Petri net that we can use for process modeling. You have such a workflow net in case you have an input place and an output place. That's the first 2 conditions. The input place means that you have a single place with no incoming arc. Right? So you see the definition of a start place, or also called a source place or an input place, is the fact that you have in your entire model only one place which has no incoming arc, only an outgoing arc, or multiple outgoing arcs. That's fine, but only one place has the characteristic that it has no incoming arcs. And the same holds for my sink place. In the model, I also have one place where I have no outgoing arcs, and only one, right? That's what we would define as that's already two characteristics that we need in order to define a workflow net. Note that that's a bit different from, if you know something about BPMN, typically you are not really bounded in the amount of start events in BPMN, and definitely not in terms of the amount of end events. Not that these places represent events, by far not. They are not events, so that's a bit confusing between Petri nets and BPMN. But still, the fact that you have this kind of source and sink make that these places somehow represent the start and the end of the process, right? And therefore, you can kind of see it as Petri nets, and especially workflow nets, restricting the start and the end of a particular process, right? We're not yet there. The most complex characteristic of a workflow net is not yet defined. I will define it here. It says that the net needs to be strongly connected, right? Strongly connected, which means that every pair of elements, places or transitions, doesn't matter, but every pair of elements should have a directed path in between them. Directed meaning you cannot go against the direction of the arcs. So which means, for instance, A and E need to be on a directed path. A directed path doesn't take into account the firing semantics. You just have to find a path, a directed path, which in this case between A and E exists. The problem with this definition is that there is a hidden assumption, because suppose that I ask you every pair of activities, suppose that I say, is there a directed arc or a path, a directed path between E and A? No, there is not. A directed path, I cannot go back, so there is no directed path between E and E. So you could say this is not strongly connected. The problem with the definition of strongly connected is that it assumes that you take into account the so-called reset transition. This is a reset transition. This is an invisible transition, something that has no meaning for the process, but it's a transition that connects end and start place. And it allows to reset your model. Therefore, we call it the reset transition. But you need to, in order to check the strongly connected property, and only then, you need to assess and know that this reset transition is inherently part of such a model, right? But checking those three different characteristics requires you to look at a different, well, not the same model, but for the last characteristic, you need to take into account the reset transition, while for the other two, obviously you don't, because if you draw the reset transition, the end place doesn't fulfill the definition anymore of my end place, right? Of an end place. So this reset transition is only something that we use for some purposes. One of them is it is to check the strongly connected property of a net, right? So this makes that we have a directed path between, for instance, E and A, right? Because we can go from here like this to A, right? That's what you need to remember. But this reset transition is not by default part of the model. It's a kind of an implicit part of the model. You don't draw it usually, but you need to be aware that if there's a workflow net, sometimes, for some purposes, you need to take into account this reset transition. All right. To just give you a counterexample, suppose that I drop this C4 place from my model, then we lose the workflow net property. This model is not a workflow net anymore. Despite the fact that it contains a start and an end place, the strongly connectedness property is not fulfilled. Why not? Well, try to give me, even with the reset transition, try to give me a directed path, for instance, between D and B. It's not possible. It's not possible anymore. Even with the reset transition, if you would draw it in your mind, like you would draw the reset transition, whatever you do from D, you can never reach any other element anymore, because it has no outgoing arc, so from D, you have no option to connect it to any other element, right? Okay, good. Now I move to BPMN. As I stated, BPMN being an OMG standard, has attained the status of the most prominent modeling language for business processes. Wherever you look, there are still other languages used, for sure, but the majority of process practitioners, process management practitioners, will use BPMN. It has somehow gained the upper hand amongst all the modeling languages. Also, it is supported by a very wide range of tools. In this course, I will mainly let you work with Signavio, which is an online editor, which works fine for most of us, but you're actually free to use any editor. I don't really want to restrict it, but I know Signavio quite well, so I can give you better support for that one. With respect to other tools, it's a bit more difficult sometimes. And especially I would avoid from, for instance, using Visio, because it doesn't contain the same functionality as you have in Signavio. In terms of modeling tools, Signavio is definitely the more advanced tool, which also, for instance, supports automatic syntax checking, which you don't have typically in a tool like Visio. So it's not a bad thing, and also because it's an online tool, it's a browser-based tool, whatever you use in terms of system, you can use this tool. There is never a problem with it. You don't need to install anything, so that makes it easy. That makes it easy to use. And also, I will provide it on Toledo, or it's already there, I guess. I provide you with an access link, which makes that you can use that tool entirely for free under the academic license. All right, BPMN. BPMN in terms of elements, well, if you would look from very, very far away, it looks pretty simple, and it would look very similar to Petri nets, for instance, right? It has events. Those are obviously not places, but you have a symbol, the same as a place, but it represents events. You have tasks, you have flows, and you have maybe one more other element, which is a gateway. That's if you look from a very, very far distance, right? So it looks as a pretty simple language. And it is a relatively simple language, except for the fact that all of these symbols have different flavors, right? This is it's not very readable, but it's on Toledo in a very, very nice and good format, so you can check it there. All these events and tasks and gateways have all kinds of specific types of versions. And that's what makes BPM quite complex in nature. On top of that, one very important finding is that if you look at models in practice, more than 80%, up to 90% of the models only use events, meaning start and end events, tasks, XOR gateways, and AND gateways. So the bunch of things that you see here are mostly not used, right? So that's already also a discrepancy between like the richness of the language, which also inhibits its practical application to some extent. And the fact that, for instance, what I mentioned last week, that knowledge of BPMN is sometimes quite limited in organizations, is exactly because if you look at BPMN in detail, it is indeed quite cumbersome to know everything. And no single process modeler actually knows all these elements. Right? I will also only request you to know a certain number of these elements, and definitely not all of them. I will clearly indicate in this session and also in next session which elements I expect you to be able to use, because in this course I want you to model, so you should know which elements are necessary to use, or I expect them that you can use them. But there are also many elements which I don't care about. A parallel multiple event, I couldn't care less. You will never find it. Why would I care? I will definitely not teach you to use an event that no one else is using. So it's part of the BPMN standard. It has particular use cases. You might maybe exceptionally once in a lifetime encounter that event in a model, but that's rather, I think it would be a joke from the original modeler rather than a particular choice of making use of the functionalities of that event. So I will make sure that I make very clear throughout the next sessions and this session which elements I want you to know. And I also want you to be able to use them then in a modeling exercise, okay? So that's the story about BPMN. So with BPMN, you can make very simple models. With start events, XOR splits, and AND gateways, and AND events, and tasks, you basically end up with very simple models, which are basically very much in line with the Petri net notation that I used before. It even also has some kind of, not exactly token semantics, but many control flow concepts and BPMN are explained using activation, activation reasoning, and this is basically entirely based on top of token semantics. So if you, for instance, have the start event, well, it basically, you can imagine that this start event creates an activation of this arc, which activates this task. It's basically a token that is produced here, and that enables this task for execution. And in XOR gateway, what you get is one of the two branches are activated, so get a token, you could say, and then activate the task that follows on the arc. In an AND gateway, you have both branches being activated, so you have basically two tokens that go into the two directions of the gateway, of the outgoing arc. So you can reason quite linearly in terms of the logic behind Petri nets and apply it to BPMN. It's relatively easy to do, and it's something that is not bad if you can do it. That's also a reason why I want you to know Petri nets quite well, because the dynamics, the execution semantics of Petri nets map quite well on the basic execution semantics of BPMN. All right, so that's what we have. So this is the basic flow elements: start events, end events, tasks, and flows, together with the basic gateways, which are the XOR gateways and the AND gateways. With these, you can already do quite a lot, right? And that's what I want to convince you of. And basically, in order to start modeling, a very good practice is to make use of so-called patterns. And in this case, I keep it extremely simple. You use patterns between pairs of activities. So if you get a scenario, if I give you a certain exercise, I describe a process in text, and the task is to build a process model out of that, well, a first good goal could be to investigate pairwise relationships, control flow relationships, between two tasks. You can basically map those binary control flow relationships, so between two tasks, into either sequential, parallel, choice, or iteration. Iteration being actually applied to only a single task, right? So if you have two tasks, they will be either sequential, in parallel, or in a choice construct. And sometimes you might also need to detect that an activity can be repeated, and that's what we call an iteration. Well, these four fundamental building blocks, they can be modeled very easily. Let's look at the most common pattern that you have between pairs of activities. It's a sequential relationship. It's a mandatory control flow relationship, which makes that one activity cannot start before the other one has ended. That's what we model in a Petri net on top, like this, right? In this case, the Petri net notation, B cannot start before his A is finished. Why? Well, B needs a token in its input place. This token can only be created by firing A. So this makes that there is a strict control flow relationship between the two. The corresponding notation in BPMN is this one. So it's quite similar. The only thing is that here we don't have this place in the middle, but an arrow in BPMN between two activities basically has the same meaning. It means that this activity cannot start before this one is ended, right? That's simple. Sequence pattern, a sequential relationship between activities. The next one is the total opposite. The total opposite is there is no relation at all between activities or tasks. There is no relationship at all. They are not influencing each other in terms of control flow, right? This is the parallel pattern. So suppose that we have after particular A, you can do both B and C, but B and C don't influence each other, so you don't need to wait to do C until B has finished or otherwise. We basically have a parallel pattern between B and C, which is modeled in a Petri net, as I showed you before in the example. After transition A, you basically have two outgoing places, and they basically create two parallel branches in the model. A parallel branch, because this place will get a token, and this one as well. So B and C can basically execute at will, irrespective of each other's execution. That's the logic behind it. And that's also modeled in BPMN with this end split gateway. right? This end-split gateway is exactly the same construct as the PetriNet construct above, but in BPMN notation, obviously. So you execute A by, you go to this gateway, this parallel end-split gateway produces or activates both branches, which means that both B and C can be executed without any relationship between those two, right? Note that in BPMN it is possible to shorten this notation to this. You can actually drop the gateway, so you can actually use the right-hand notation, but I actually discourage you to use that one. I encourage you to always show your gateways, mainly for understandability purposes, but also because it allows you to model in a more block-structured fashion. Block structuredness is something I will come back to later, but by dropping this gateway, you might turn your model in a more difficult to understand model. So I always prefer you to use the gateway, although this is entirely acceptable from a BPMN standard perspective. But try to always use the gateways, even if you don't need to. If you have a split, you also need to join these paths or these branches. So that's why we have a synchronization pattern. So a synchronization pattern refers to the fact that parallel branches are synchronized, are brought together, and that's what we do with an end join. In PetriNet notation, that's basically a transition with two incoming places, right? That will create or make D into the synchronization transition. You can only fire D if you have tokens in both these places, and therefore D will wait until both places get a token, and therefore D acts as a synchronization. In BPMN, the synchronization is performed through the gateway again. So the gateway will state, or this gateway states, that you need both branches to be activated. So you have B finishing, activating, but this will not continue until also the lower arc or the lower branch is activated, right? So after finishing C. So therefore, you model the same thing. So this is the end join gateway. Please, in an exam, although now you don't have to write anymore, but in previous exams, I had many students writing end joints, which is not really correct. That some of you might be thinking about this on an exam, but it's an end join, yeah? Not with a T. Yeah? Okay, good. Next pattern, the final pattern between two pairs of activities. So we had sequence, we had parallel, we have choice, the third one. Two activities can be in an exclusive relationship. You do either the one or the other activity, right? That's what we call a choice or an XOR split. In PetriNets, this is a notation, so one token serving as the input place of multiple transitions. In BPMN notation, we have obviously the XOR split. The XOR split modeled here. After splitting, you also need to synchronize or merge. We call it a merge because it's not really a synchronization. You don't need to wait. You don't need to synchronize. You just bring the paths back together in the model, but they will never be activated at the same time. So basically, in PetriNets, this is this notation. So two transitions with one output place, which makes that as soon as B or C is executed, D can also execute because it will have a token in this place. And in BPMN notation, this is the appropriate notation using the join gateway. So this is the XOR join gateway, joining two exclusive paths or more exclusive paths towards the further part in the process. Again, like with the end split gateway, there is an alternative notation without the join gateway, but I still prefer this one. I still prefer you to always model your gateways, which makes that in some cases you model gateways one next to each other, but I prefer you to suppose that I have like these paths joining, but after this one, I have another choice, right? Suppose that I don't D, but I have a choice between D and E. Many people would just model two outgoing arcs here, which makes that this gateway will both serve as the join, the merge, as well as the split for the next part. Well, that's something that I discourage. I would use two gateways, right? next to each other. I would model another split gateway and then the two activities that model the split. Right? It's my advice to you. As I mentioned, in this course, I try to give you a bit more a modeling perspective, like how to model. Well, one of the key things to model well is to keep in mind the understandability of your model, the reuse of your model, the understandability of your model by non-experts, by people that didn't help you to make the model. Well, those kinds of tips and tricks help you to make models that are better understandable and more reusable. All right, and then we have the structured loop pattern. Now I come back to the question of the gentleman in the front. He asked, like, how do you model loops of activities, right? Well, in Petri nets, I have to be honest, there is no easy notation. The only way that you can denote this in Petri nets is through using a so-called invisible transition or a routing transition or routing transition. It's a transition that's only there in order to reroute the model, right? But it has no corresponding business activity. So that's why we call it an invisible or a silent activity. It has no corresponding business activity. It's only there to add to the control flow to reroute the model towards a particular state. That's what you see modeled here. So we want to do B multiple times. We want to allow that B iterates, right? That you can do B and then B again. Well, therefore you need this construct. What you will basically have after B, and that's also what you basically have in the BPMN model, I will explain in a minute, but you basically have a choice after B. After every execution of B, you will make a choice between either doing C or doing B again. And that's actually what you model with this invisible transition. Because you will have a token here after B, right, in this place. Well, if you fire the invisible, what you will do is consume this token and produce a token here, which will enable B again. And if you do C, you will consume this token and you will not be able to do B again. So that's basically the notation, the short notation, but still a bit more complex than you would expect in Petri nets, in workflow nets, in order to model a single loop, a loop of length 1, as we call it, right? Because iteration and looping in processes is actually commonplace. It's actually something that happens a lot. In BPMN, in the standard, they opted to allow more flexible and more convenient modeling notation for this. And a convenient modeling notation is this marker, this loop marker. This small arrow allows you to indicate that a particular task or also a sub-process can be repeated, right? It has the same meaning. It's basically an invisible choice, an invisible XOR split that makes a choice between either doing C or doing B again. Because I will show you later, when I show you the notation of this, when I talk about iteration at the end of the lecture, it's basically like a choice. It's a choice between either doing C or doing B again, right? So it's exactly the same, only this loop marker shortens the notation and makes it more convenient for people to use. And which is a good thing. That's one of the key advantages of BPMN. In some particular ways for modeling, it has notation that is shorter and sharper to denote particular types of behavior. And this is one very good example, where other modeling languages have much more difficulties to model it in, with the same kind of ease, I would say. Right? Okay, before the break, I now introduced Petri nets. I very shortly introduced BPMN, but after the break I will continue with this. What I just want to mention before the break is also just 3 more slides, 3 more examples of other modeling languages. You don't need to know the basics of it, but there is a couple of languages that I want you to at least have heard of, right? That you at least once in your life came across these terms. The first one I want to point out, because exactly this difference between Petri nets and BPMN, BPMN being an extremely useful, user-friendly and extremely convenient modeling notation, while Petri nets has more the kind of the sound and ultimately correct notation. Well, the YAL language, the yet another workflow language, is a language that actually combines both parts, both advantages. It both has a very interpretable notation, through, for instance, including gateways explicitly in the model, right? As well as the same formal foundation as Petri nets. So that's one example of a language, and there are other examples, but in academia, in research, there are many examples of languages that try to come to a language that is as good as possible with respect to both user-friendliness as well as theoretical soundness. Because in practice, you find a lot of modeling language, some of them which are extremely useful, but they are not good enough in terms of sound modeling, always making sure that you know what kind of behavior you have. And on the other hand, no one in practice is interested in using Petri nets as a modeling language. So you find many languages like YAWL that try to strike a balance between both, that try to have the full mathematical soundness as well as ease of interpretation. And one of the ways through which YAWL is creating this ease of interpretation is by explicitly modeling splits and joins. Right? That's what you see here. Another language that I want to show, and that's more from a practical viewpoint, is EPCs, or Event-Driven Process Chains. It's another quite popular language in practice. Why? Well, because of the use of it in SAP. SAP, as of version R3, all the processes that are defined in this ERP software were modeled in EPCs. So not in BPMN, not in Petri nets, but in event-driven process chains. You don't need to know the notation. I just give you an example of such a model to have a visual recognition of it. It basically works through also to gateways, you could say. These circles here are gateways, but also events. It's entirely based on the concept of events. That's why we call it an event-driven process chain. What you have to know is that the developer sold this language, sold the ARIS tool, which developed this language, to SAP, and SAP decided to use that modeling language throughout its ERP implementation. That's why still today, if you would, for instance, be an SAP consultant, and you want to change or customize certain processes, in many cases, you are confronted with these EPCs. All the standard processes in SAP are mostly still modeled in EPCs. They now, in recent versions of SAP, they also allow, for instance, modeling it in BPMN. But in earlier versions, and you still have many companies that work with earlier versions of SAP, you still find event-driven process chains across the board. For all the standard processes, you would need to look into the EPC to understand the model. And that's why I want to just give you this information. And then finally, the final notation I want to mention is a so-called transition system. Because I talked about Petri nets, and Petri nets are already a quite advanced language, but in terms of dynamic systems, there is another type of notation for dynamic systems which is often used in information systems and also in any kind of application. That's a transition system. A transition system is also a dynamic modeling language, but it's approaching the dynamic part of it through states, right? I already referred to states when I talked about the Petri net, because every mark in my net refers to a state. But in a transition system, you will basically model these states explicitly. I now made a mapping between this Petri net that I used before and the corresponding transition system. Well, this transition system models states explicitly. That's why we call it the finite state machine, or also a transition system. This is still a popular modeling language in many environments, in many systems, right? A state-based or a transition system-based modeling of objects is something that you still come across in many, many different systems. That's something I want to mention. Why is it not used a lot as a process modeling language? Well, the reason is that this is still a small model, and the corresponding transition system is also still small. But as soon as you have a larger behavior, meaning more parallelism, more loops, right? This transition system typically explodes. The amount of states grows exponentially, and it's not useful anymore to model this. If you have a small-scale object lifecycle, it's sometimes easy to use this state-based approach because it's very intuitive to model like this. But a full-blown process model denoted in a state space or denoted with a transition system, it just doesn't scale. It's not user-friendly, it doesn't fit, not on a slide, not on an entire building. I mean, it would just explode. So it's sometimes still used in the background to do analysis, this state transition system or this this finite state machine, but it's not really used as a true process modeling. So in the remainder of this session, as well as in next week's session, I will provide more details about the BPMN language. I will provide you with more complex constructs, let's say, that allow you to model or use the modeling language of BPMN for more particular types of control flow situations. But I expect that you can already use these main elements, which are start event, end event, and also gateways and tasks. The main gateways, which are XOR splits or XOR gateways and AND gateways or parallel gateways. I will now expand on this. I will start with one additional control flow gateway that I want you to be able to use or know. I don't necessarily claim that you need to use it. I would just one gateway, one additional gateway that I want you to be aware of. That gateway is the so-called inclusive OR. So, while the other two are quite clear, in an exclusive gateway, you pick one out of many paths. In a parallel gateway, you pick all the paths. Now, in an inclusive gateway, you pick one or more, but not necessarily all. You can also pick all. So it's the most flexible gateway that exists, basically. So it is typically used to model the concept one or more, right? A good example is given here, a very small example, but suppose you get an order in, like you receive an order, and in this order, multiple items are listed. Depending on where these items are sourced, are stored, you might need to check availability in two different warehouses. So if this order contains items of warehouse A, you will need to do the upper branch. But if the order also contains items of warehouse B, you will need to do the lower branch. And it is possible that your order contains items from both warehouses. So it is possible in certain situations that you do both the check availability in warehouse A and in warehouse B. This is a particular modeling construct for which you can use this OR gateway, the inclusive OR gateway. So it's another gateway I want you to know. The thing is that this OR gateway is often misused or even abused. It's really a very, very flexible gateway that can sometimes help modelers which don't really take into account typical modeling guidelines, right? One of the ways to use the model is illustrated in this slide. This model is syntactically incorrect. It contains a so-called deadlock. A deadlock is a situation where the model cannot continue. So the deadlock is here, exactly at the second end split, or end join in this case. So this end join, we have a deadlock there. What is the deadlock? Well, we start the process, all fine, we have an end split, both paths are activated, we do this task, we do this task. After they finished, this synchronization happens, we continue. But then here, in case we do the loop, we have this condition, we go back, we do this activity, right? We enable this one, but this is an end join. It needs inputs on both arcs, and it will never get it. It will never, ever be possible to execute, identify availability, or identify variability again. So therefore, here it deadlocks. What you now could do, I didn't draw it on the model, but replacing this AND join with an inclusive OR join solves the problem. Because an inclusive OR join can be used to, well, whenever in a situation you have only one incoming arc that is enabled out of both, it can also continue the process. So in some cases, such an OR join, inclusive OR join, can allow to continue with less inputs than the AND join would request, right? So that's a solution. This is something that is very, very ugly and really not recommended from an understandability perspective and also not really from a syntactical perspective. But you could use the inclusive OR in that way. I prefer that you don't use it except for the case where it is a one or more situation. And in that case, you mix and match an inclusive OR split with an inclusive OR join. It's as simple as that, right? So you will always use this gateway in a block-structured fashion, and only in those cases where you have a clear one or more case. In other cases, like please don't, I encourage you to not use this OR gateway because it mainly increases the complexity of your model, and it's usually not necessary unless for this one or more case, okay? All right, next, I have two more topics that I want to talk about in this class. The first one is hierarchical modeling or decomposition. The second thing is something more about iteration and loops. So first, decomposition, also referred to in BPMN as sub-processes. Using sub-processes is something that is also a key practice in BPMN, and is also, again, if you compare it to Petri nets, a key advantage of BPMN. In Petri nets, you don't have this opportunity to separate out your model in a hierarchical tree of models, in a hierarchical structure of models that allows you to look at more simple models at the top level and to specify, if you want to know more detail, you can go and look in more specific parts of your model in the sub-processes. So it's another choice of BPMN next to, for instance, this loop marker and the iterations that makes that BPMN, for many practical situations, is a much more handy language, a much more convenient language, and so these sub-processes are a key part of it. Sub-processes, I might ask you, this type of process model, it looks perfectly fine, it's well structured, it's nicely laid out, it's quite good to understand, but still, I would argue that given this structure, you could optimize the model. You could optimize the model. I cannot give you extreme examples. This is actually not an example where I would explicitly demand you to use sub-processes, but it's just to give you an insight in when you should try to do it. Well, if models grow, and this already becomes quite a big model, not yet, but still, it is on its way, let's say, it is a very good practice to try to identify parts of the model, so a subset of tasks and control flows between these tasks that you can single out in a sub-process. So that's what you then typically do. So you will single out, oh, well, I skipped. Sorry, my pointer is. So you will single out parts of this process. So this is better. This is better because it's more easy to interpret this model. And you can single out particular parts of the model. So you'll basically single out this part, single out the bottom part, and put those parts into separate processes, which we call sub-processes. And being able to do so allows you to, at the top level, at the so-called refactored model, that's the name for the model where you replace these parts with a sub-process notation. So this is the refactored model. In this refactored model, you replace these sets of tasks and control flows with a corresponding sub-process indication, which is basically an activity that invokes this sub-process. So it's a kind of, you could see it as a fake activity, or we call it an invocation activity that invokes, that calls the sub-process, that activates basically the sub-process. So this is the model, or well, the model with the sub-process identified. This view that I show here is also a view that you can have, where you have basically the sub-processes being expanded upon. So this is called the expanded view, right? This is the expanded view of the model, and this is the refactored view of the model. The refactored view is the model view where you have the sub-process modeled. But in some cases, and also Signavio allows you to do is, you can show also the sub-processes in the main model. Then we call it the sub-process in separate diagrams, as is represented here, right? So those are two choices that you can make. Typically, the most obvious choice, also for an assignment, for instance, is always to show the refactored model and to show the sub-process separately from the parent process, right? That's the default choice. But you can also represent it like this with the expanded sub-processes. These are expanded sub-processes in the parent model. So refactor model, I talked about this. Now process decomposition. So I already mentioned this, so you'll replace a sub-process, or you will create a sub-process and have an invocation activity in the main process, or in the parent process. Why do you do this? Why do we apply process decomposition? Well, I already explained one main reason, which is this reason here. You break down large models into smaller ones, which, again, affects the interpretability of your model. So interpretability or understandability is a core reason why you do this, right? And if I make you model in the assignment, you will see that understandability is the first evaluation criterion. Even syntax for me is not more important than understandability. So that's why process decomposition is one of the key things. I don't claim that you are obliged to use this in any exercise, and also not in the assignment, but I can guarantee you that it eases the interpretation and it affects the interpretability of your model. So that's one very important reason. The second reason is explored in the subsequent slides. It's the fact that by creating sub-processes, we can also increase reuse of these sub-processes. I will explain it in a minute, but we can reuse process fragments by creating these sub-processes and make them reusable across different parent processes. And a third reason is more from a control flow perspective, in terms of, for instance, repetition and also exception handling, right? So these two are both repetition-related reasons. This is exception handling-related reason. You can apply particular operators, events, or gateways at the level of a sub-process. You can, for instance, allow the repetition of a subset of tasks through such a sub-process. Or, in the context of exception handling, you can allow the exception of a particular type within the context of only a part of your process. And you would use a sub-process for that with an attached boundary event to that sub-process. So another reason is that from a control flow perspective, you can apply certain functionalities at the level of a sub-process and therefore apply it to a sub-part of your model. So that's the third reason. I will come back to the second reason, the reuse. The reuse case, well, this is process hierarchies. I will explain that later. What I first want to explain, so I will come back to slides 43 and 42. What I first want to explain is reusable sub-processes, or to be exact, shared sub-processes. That's the term that is used in BPMN. Shared sub-processes are sub-processes that can be used across different parent processes. In a normal fashion, a sub-process can only exist within its single parent process. So if you don't have that particular parent process, you can't have a sub-process. But shared sub-processes can be reused across different parent processes. So you can reuse it whenever you want it. So it's basically a reusable component that you can plug into different processes. That's what we call a shared sub-process. At the refactored model level, we indicate that a sub-process is a shared sub-process by this fat rectangle. This fat rectangle is also basically an invocation activity, but an invocation of a shared sub-process. And therefore we call it we have a special name for these activities, they are call activities. So that's not a standard invocation activity, this is a call activity. Right? So this signed loan sub-process is shared across multiple models, and so has multiple parent processes. Right? So this is what I just said. So the sub-process is by default embedded in the parent process, except for the fact when you make it reusable or shared. In that case, you use a call activity, and this call activity reflects that the sub-process is global, so it can be used across all kinds of different parent processes. So this is the example again. So this sub-process exists within both parent processes. I want to come back to my slides on process hierarchies. I already talked about process architectures in the previous session. Well, this hierarchical modeling is obviously something that is commonplace in many organizations, especially in mature BPM organizations. Hierarchies of multiple levels exist. I will never demand you to model at the level of, well, level 4, 5, 6 deep. That's never going to happen. The maximum is that you have one parent process and a number of sub-processes, but you would never go deeper in terms of the hierarchy. But in many situations, in many companies, they do try to attempt to get to a reasonably large process hierarchy, where basically at the top level, you have almost like a value chain, right? The main parts of your organization are modeled at the top level, and they are then split out into separate processes, right? At different levels, right? That's what we call a real process hierarchy. That's when, once we start talking about level 3, 4, 5, then you really can talk about a process hierarchy. Regarding modeling guidelines, well, such a top-level process, even in a 2-layer hierarchy, is preferably as simple as possible, which means that in the top level, using sub-processes makes that you have as few gateways as possible. That's basically the kind of reasoning that you can apply. So you try to make it almost into a value chain. It's not always possible, but you try to reduce the complex. A value chain is just a sequence of activities, right? So, or a sequence of sub-processes. You try to limit the amount of gateways in your top model as much as possible, typically. Not always, but typically. Then another guideline regarding when to use those. Typically, that's subjective. This decision is subjective. Many people argue, like, as soon as you have 30 elements, or 40, or 50, you need to split up. In the modeling guidelines that we will see in a couple of sessions from now, this 30 is replaced by 50. So I put 30 here on the slide as just a number. There is no fixed rule. But for many of you, I would argue that as soon as you reach 30 tasks in a model, there is really a genuine chance that hierarchy and decomposition will improve your model, right? But basically, it's a judgment of the modeler. It's a judgment in terms of interpretability. Note also, and that's the final thing I want to mention, and that's also something I will come back to later, size of models has a very significant impact on errors in the model. Like, we know from research that the larger a model becomes, the more likely it contains errors. So that's another warning for you as a novice modeler. As soon as you make the model large, there is an increased chance that you make mistakes against the syntax. So also for that reason, it's quite important to think about hierarchical modeling. All right. So the call activity, I mentioned this. I think this should be clear. Syntactical rules. Oh yeah, that's the final important part. Syntactical rules. We create sub-processes. But the sub-processes that I showed here, this is not yet a sub-process. This is just a slide where I indicated which activities should be grouped, but the actual sub-processes are drawn here. And what do you see here? Well, every sub-process starts with a start event and ends with at least one end event, right? So you can never ever draw a sub-process that isn't a process. So you always need a start, at least one, minimum one event, and also at least one end event. You cannot have a process without start and end event. Okay, so that's one aspect of syntactical use of these sub-processes. Another important aspect, I'm going back to the slide. I'm sorry for the wait. Another very important rule is that sequence flows, control flows in the model, can never cross sub-process boundaries. So you can never, ever cross the boundaries of a sub-process with a control flow. You can only cross boundaries of a sub-process by means of message flows, and even those crosses are really not, I mean, it's not advised to do it. It is allowed, but it's not really something that you typically do. But it's very important to retain already, because these sequence flows or these message flows only become important when we talk about pools and lanes. But in the case of where we are now, it's just very important to understand that you can never ever cross sub-process boundaries by means of sequence flow. So if I go back to this model, here, it would never ever be possible that it would say like, okay, from this sub-process, for some reason, I need an XOR split here that goes back there, right? Or that goes back to the model, to the parent model. That can never ever work. That's not allowed, okay? Good. But message flows are allowed to cross boundaries. It's typically something that you also want to avoid, but that's more from a user-friendliness perspective. Okay. Any questions regarding this hierarchical modeling? Yeah, there's one more. Wait, there's one more thing. This bullet point regarding end events, that's also one thing that I want to mention, but I will come back to it next week. If you have a particular process, a sub-process, with multiple end events, in this case, quote accepted and quote rejected, it is advised to make sure that in your parent process, you account for these different outcomes. You cannot just in your parent process, after the sub-process, continue without acknowledging that you had two different outcomes. I actually deem that this is a syntactical mistake if you don't do it. So the typical way to solve this is by introducing an XOR split after the sub-process with, on the args, the conditions that relate to the outcomes of your sub-process. I will come back to it next week because there is an alternative modeling variant that I will explain next week based on boundary events. But so remember for now that as soon as your sub-process has more than one, so two or more outcomes, you need to catch this, in your parent process. You cannot just continue your parent process without taking this into account, right? So therefore, one of the options, it's one option, but it's an often used option, is to make use of this XOR split after the sub-process, okay? So that's one additional syntactical guideline for modeling sub-processes, but this is something I will come back to next week. I will come back to this next week. Be assured. That's something that I will take up with you again. All right, and the final part for today is a bit more information regarding sequential or parallel repetition. So iterations at the level of a single activity or sub-process, or in parallel, also at the level of an activity or a sub-process. So let's look at sequential repetition. So the difference between sequential and parallel repetition is that in sequential repetition, a task or a sub-process reiterates, so happens multiple times, but in time, the repetitions follow each other. They cannot overlap, right? So you have task A being executed the first time. When it stopped the first time, you can execute it the second time, a third time, and so on. That's sequential repetition. There's also a parallel version of repetition, which makes that all the iterations, all the executions of a particular task or sub-process can be executed at the same time. That's what we call parallel repetition. I will explain it in a minute. But let's start with the simplest form, the sequential block-structured repetition, right? As I already indicated in earlier slides, in BPMN, you have a very convenient notation for this. It's this loop marker. A loop marker that can be applied to the level of a task or to the level of a sub-process. And it just indicates, basically what I said before, that you have the choice after executing this task the first time to execute it once more or to continue with the rest of the flow, right? So that's the loop marker being used at the level of tasks and sub-processes. Note that in typical models, and this is an example where I use this, in typical models, it is, well, required, I see it as a syntactical mistake if you don't add the condition which makes that you iterate or not. It's basically the same as with an XOR split. If you model an XOR split, I always expect that you put the data conditions on the args exiting the XOR split. Well, the same holds for a sub-process or for a task that iterates, that loops. If you have this loop marker, I always expect that you as a modeler add the data condition which I need to check and which the model or the system needs in order to know whether the iteration happens or not, right? So that's the, until response is approved, that's the data condition that makes that I know when this loop will terminate, will end. Very important to know, I consider this a syntactical mistake if you don't add this. Also, if you model me an XOR split without the data conditions, I consider that a syntactical mistake, because then you don't acknowledge the fact that in a system, in an implementation of this process, I need to know what data I need to consider in order to know which direction you will go or which choice you will make, right? So that's what you need to remember. This data condition this is a simple text annotation. And this is something that is not mandatory in BPMN, but it's something that I demand, and you just need to add it as a text annotation to the task or to the sub-process to which you append this loop marker. Typically, and that's indicated with this call-out at the bottom right, typically this data condition corresponds to a particular task or activity in the sub-process which changes this data element. And this activity or task is what we call the decision activity. Right? This decision activity is the activity that manipulates or affects the data attribute that is considered in the data condition of my loop. All right, next is the parallel repetition, or a multi-instance activity, right? Or multi-instance subprocess. Again, both flavors exist, both for multi-instance tasks as well as for multi-instance subprocesses, so you can apply this marker to both. This marker is obviously different. It's this marker that I'm talking about, so these three vertical bars that you add to a task or a subprocess. This symbol indicates that you can also repeat this task or this subprocess, but in a parallel structure. Meaning that the repetitions can occur at the same time. So you don't need to wait for the previous execution of my task before you can start the second, the third, and so on. Typically, for a multi-instance task, or always for such a multi-instance task, you know how many instantiations need to occur before you start the first one. I will give an example in a model that's easier to see, right? This is something that a novice modeler might model. Suppose that there are 5 suppliers, right? You need to obtain a quote from 5 suppliers. You can model this with an AND block, with a parallel block. This is an example where it is more convenient to use this multi-instance activity. A multi-instance activity, because this obtain quote activity, I modeled it as a sub-process, but it could also be just a task, is executed for an object, in this case a supplier, multiple times, and these multiple times that this is executed are not restricted, are not related to each other in time, right? So you can do the quote, obtain quotes from supplier A, irrespective of when and how you obtain the quotes of the other suppliers. So that's why we use a multi-instance. There is no reason why you would model this with a loop marker, because there is no strict ordering. You don't need to do A first, and then B, and then C, and then D. No. Your model doesn't need to specify this. So it's a more flexible form of repetition. Typically, this is used to be applied when this task takes an effect on an object which is not the main object in your process. So in this case, my supplier is actually a sub-object, another object in the process. The process is at purchase order level, right? And this multi-instance activity is specified at the level of a supplier. So it's oftentimes in the case where you have an object, a sub-object, so not the main object that you're modeling, but there's a sub-object in your process for which you need to do something multiple times. In that case, you often use this multi-instance marker and a multi-instance activity or sub-process. Again, this cardinality is for me a mandatory part of your model if you use a multi-instance marker. It's a text annotation again, but it's something that I deem necessary in order to understand your model and to judge your model in an objective way. So if you don't add it, I miss information. I don't think your model is syntactically complete. Yes, a question. Sorry? How do we know from this how many suppliers? In this case, I suppose that task before this determine how many suppliers you have, or the data environment of your process will know this. It's just that you need a data object to which this condition can refer to. In this case, I assume that the number of suppliers is known before this obtain quote activity, right? So it's not like in the previous case where in the sub-process you had a decision activity that actively manipulates the data variable. Huh? It could be, it could be. It could be, I have examples in modeling exercise where I say like, you need to contact 10 witnesses, for instance. Well, 10 witnesses, then you know in the activity before the one that you are doing, you know that you need to contact so many witnesses, and in the next one, you know it's 10, you exactly will have 10 repetitions or 10 multi-instance executions. But in this case, I just have a kind of a more abstract representation, but the supplier, the number of suppliers, is a data variable that will be known in the context of the process. You can see it as a kind of a global variable in this case. A global variable that is available in the process. Okay, but usually, I mean, no, not usually, always, in any case, you know exactly how many times you do obtain quote before you do the first execution, right? Before you start this multi-instance activity, you know exactly how many instantiations need to happen. That's different from the loop marker. Eh? There you don't know. There the looping is determined by the loop condition, by the condition. It's not fixed beforehand. It's not fixed beforehand, but with this it is. Note, and now I make it a bit too complex, and I explicitly didn't add a slide about this, but BPMN also contains the flipped version, the sequential multi-instance task. That's very similar to the structured loop, to the loop marker, but in that case, you still specify the fact that you have a certain number of instantiations that will happen sequentially. Right? So it's a symbol, the symbol that is denoted. Oh, well. So if I have a task and I model it like this, right? So instead of vertically, I put these bars horizontally. It's also a multi-instance task, but it's a sequential multi-instance task, which means that the iterations, again, happen sequentially. The difference with the loop marker, right? The difference with the loop marker is that in this case, it depends on my data condition, right? How many times I do this loop. While in this case, in this particular case, the number of iterations is determined as soon as I start this multi-instance task. But the instantiations itself will happen one after another. Right? So if I have three iterations of task A, they will happen sequentially in time. If this is time, right, they will happen sequentially. While for a regular parallel multi-instance task, well, if you have time and my instantiations, well, they can be like start and end like this, right? And potentially even like this, I don't care. There is no relationship. Suppose that I have 5 in this case, 5 iterations, they can overlap in time. That's the parallel multi-instance. This would be the sequential multi-instance task. But I actually don't expect you that you know this one. I only want you to know the multi-instance parallel and the loop marker as a sequential, okay? Good. I'm almost there for today. I have 5 minutes left, I hope. I don't need 5 minutes. The final slide about repetition is this one. It's a so-called ad hoc sub-process. I also consider it to be a repetition. I will explain in a minute why. But first I want to explain to you that this is probably, out of all the notations that I will introduce, the most complex thing to understand. Although it is not crazy difficult, you might make this extremely difficult to understand what is happening. This is, well, it's this marker that is important, this tilde marker as we call it. This is a tilde marker indicating that this subprocess is an ad hoc subprocess. An ad hoc subprocess is the only subprocess that doesn't need start and end events. So it is already an exception in itself being a sub-process, because all other sub-processes in BPMN will always require a start and an end event, but this one doesn't. On top of this, in this ad hoc sub-process, you are free to connect activities or not, and in terms of execution behavior, this allows the most flexible option. Basically, in this sub-process that is drawn here, you can do whatever you like. You can execute all of these 4 activities which are modeled here as many times as you want, 0 to n times, even not. So basically, you can also have a sub-process, an execution of this without any activity executed. Right? So this is the most flexible notation in BPMN. If for a certain part in your process, you have no restrictions whatsoever regarding the control flow of a certain number of tasks, obviously not of everything, but a certain number of tasks, you have no clue. It can iterate, it can happen multiple times, it can happen only once, there is no order between these, you don't need to do evaluate prior performance first and then assess financial stability. No, you can do it in whatever order, then you can use this ad hoc sub-process. Oftentimes, and that's also something that Professor Vantine will tell you in the other part of the business analysis course, oftentimes process modeling, this type of process modeling, especially using BPMN, is considered to be not friendly for flexible processes, for unstructured processes. Well, this is one part of BPMN which does allow for flexibility. Some flexibility. This is quite extreme flexibility, but still, there are elements in BPMN which allow you to create more flexible processes, and this is one of them. It's the so-called ad hoc sub-process. I consider it here because without indicating it at the activity or sub-process level, these activities in the ad hoc sub-process can iterate as many times as you want. And that's why I put it here. So although that I don't draw it, I don't draw a multi-instance marker, I don't draw a loop marker, the fact that I have this tilde marker denotes it an ad hoc sub-process, and because it's an ad hoc sub-process, all the tasks in the sub-process can execute it as many times as you want, right? So that's why I put it here. Sometimes, I mean, I have it here on the second bullet, you still might define some sequence relationships. Suppose that I draw an arc between this activity and this activity, you should interpret it as you interpret an arc in another part of the model. So it means that if I want to assess financial stability, I need to do evaluate prior performance first. So should there be an arc between those two? In case I have an arc here, in between those two, then I will need to do this activity first before I can do this activity. But I could do it multiple times. It will only restrict the fact that I cannot do assess financial stability before I executed evaluate prior performance. Okay? This is definitely the most complex modeling element, or according to me, this is the most complex modeling element that is available in BPMN. But I still want to show it because it's sometimes useful for modeling flexible processes. And it's also something that I want you to know. When people would criticize BPMN from the perspective of like, you cannot model any flexible things with it, it's not true. You can, but it's a bit more complex than how people usually use BPMN.